And I guess one real big question I have, do any of you able to get in touch with anyone else in the class? I mean, this is the most we've had. The first day, of course, I gave you very little warning on that one. No one was here, and then Thomas was here the last two classes, and now we finally got a second person here, but I don't know where everybody else is. Most of my other classes are picking up in attendance, and I guess this one is since it's doubling, but I still have way more absences than I have presence. Can y'all get in touch with any of the other people in the class? Do you have any way of doing so? Did y'all exchange phone numbers or anything? It takes silence to mean nothing. Okay, David, can you hear me yet? Well, if you can, that's okay. I just can't hear you. And Thomas, have I still got you?
Yes, sir.
Okay,
I think
good.
so.
All
My
right.
mic is still having problems, though.
You think so? Because I do every now and then see something flash in the corner, which I...
Yeah, I also have a bad internet connection.
Oh, you do? Okay. Well, mine seems to be connected now, but earlier it was having to reconnect and reconnect, so I guess we're okay. All right, now, any of you have any questions on anything? How we're doing things? David, I can't remember. You probably haven't heard this one yet, so let me go over it for your sake. I hope you can hear. Since we met last time, I've gone through several different iterations of how I'm going to do things, still trying to work out what's best. Early on, I was sending announcements, things like the class and things like this by announcements. And then I found that there was a thing called messages. And I thought that was just a shortcut to doing the announcement. So I started using just messaging. Then I found out people were confused because they weren't getting the announcements. I said, well, it's not coming through. No, that's a separate thing. Yes. Is someone else here? Okay. What's that? Okay, who is this? David?
Yes, sir.
All right, good. Okay. So I thought, well, what I'll do, I'll send everything by both an announcement and by messaging. And then in one of yesterday's classes, I found out that one of the guys in the class could not receive or send any messages on the new Blackboard. And I guess the reason was he was using an iPad. He was using an iPad, and the message symbol did not even show up. So he couldn't do anything. So I said, well, I'm going to forget about messaging. I will send everything by announcement. Okay? I'll still check my messages in case students send me things, but I won't be sending anything. Well, then last night, when David, in your physical science class we're having later this afternoon, I had made up the lab. It was pretty late by the time I got to do it. Made up the lab and went to send that last night, and I found out you can't attach anything to an announcement. So I had to go back to sending messages. So I've gone through several different iterations. I had started with announcements, then went to messaging, then went to both, and then went to only announcements, and then I'm back to doing everything I send that I can send, I'll go by announcement. Everything that I need an attachment for, I'll have to send by a message. And we'll have to figure out some way to get those attachments to that guy who can't do it. I think I found one possible way to do it, but I don't know. I don't know what else to do. With him, I'll just have to get his email and email him his labs or whatever, or his test. He's not in a lab class. All right. So anyway, that's the struggles on my end. Have y'all been? Say again.
This is you, sir.
Who is this?
David.
Oh, David again. Okay, I thought someone was new was coming in the class. Okay, did you have a question?
2 people in here, huh?
Just still 2. Okay. David, did I cut you off, or did you have a question?
No, I'm good.
Okay, great. All right. Well, where we left off last time, if there's no further question, let me say this too. David, you may not have heard this. I think you probably have. But for the rest of this term, we're going to be in what we have here is what we're going to be calling, and they're going to be calling, everyone's going to try to call it this, a virtual classroom or a virtual class, okay? This is not the same as an online class. Even though you are doing it online, it's a virtual class, meaning we're meeting at a fixed time. We're meeting all together, all that can get together at that time, and we're having regular classes. Just like we were in a classroom, the only thing is we're in our own bedrooms or wherever you happen to be. Okay? So that's different from an online class, which is done for those people who can't always be at the same place at the same time, and they're just doing it that way. Those classes, there aren't many of them. They're all that we were running before, they're still going to be running. But everyone else is going to virtual classes just like this. Okay? So we're going to be in virtual classes the rest of the spring. And then the other bit of new news over the weekend was we're going to be on virtual classes in the summer as well. Now again, we're still running the online classes we had on the schedule, but all the rest that were going to be what they call ground classes, the classes that we're going to be meeting on campus, they're all meeting virtually now in virtual classrooms, just like this one, at fixed times, fixed days, and meeting together just like we're doing now. Okay, and if you're at any of mine, I'll still be using Zoom. Other instructors may choose to use the Blackboard Collaborative or Collaborate, whatever they call that one. Some people may be using that. A few may be using other things, but basically we're trying to use those two platforms. Okay, that's going to be true for summer as well. Okay. Are either of you coming back in the summer? I think Thomas said not. Is that right?
Yes, sir, that's correct.
Okay. David, are you going to be here this summer?
I might.
Okay. Well, just know that we're still working on the schedule because we had to change the entire summer schedule to reflect this virtual classes as opposed to on-campus classes and as opposed to online classes. So we're fixing the schedule, trying to adjust it to accommodate all that. And I'm going to be reviewing that schedule this afternoon after we finish our lab in the physical science class. I'll be doing that for probably most of the rest of the evening. So I think I mentioned that to you in the email I sent this morning. As soon as I can get my head above water, I'm going to get back to grading things. So right now, things are pretty slow because Monday I had either 2 or 3, in addition to 3 classes, I had either, I think, 3 meetings. Then on Tuesday, in addition to 4 classes, I had at least 2 meetings. And yesterday, in addition to 4 classes, I had 2 meetings. Okay, so I've been meetinged out, and then I'm having to review schedules today. So hopefully after today, and then tomorrow I've got a meeting, but that's in the afternoon. Hopefully I'll be able to get back to just teaching and grading and that kind of stuff. But right now they've just been eating us up with trying to work all the details out for this new process. So anyway, any questions before we get going? All right. Where we left off before, we're in Chapter 5, Analytic Trigonometry, and 5.3 is Solving Trigonometric Equations. And we've been through a couple of types of equations. We collected like terms, we extracted square roots, we factored, and that includes equations of the quadratic type. Most of these will be factoring as well. Maybe not quite as easily factored as what we did before. Those were common term factors. But let's see how we're going to do these. Many trigonometric equations are of the quadratic type, like ax squared plus bx plus c is equal to 0. The difference here, I think I've got to get my pen set up. Yeah, let me set up my pen. Okay. Instead of x's, we're going to have trig functions. Okay. That's going to be the difference. So here's a quadratic function in x. 2 sine squared x minus sine x minus 1. Okay? 2, and this is the same as 2 times sine x squared. That's just, to me, a simpler way to write it. Minus sine x plus minus 1 equals 0. An equation with a quadratic and sine. Quadratic and secant. Secant squared x minus 3 secant x minus 2 is equal to 0. Secant squared x minus 3 secant x. Okay. They just like to write it two different ways. Okay. Now, to solve equations of this type, here's what you do. First, solve for the trig function, then solve for the variable. Okay, up here, you would solve for the variable, right? Because you don't have another function in there. Here, you solve for the trig function first, and then we'll solve for the variable. So, how do you solve quadratic functions in general? Factor if you can. If you can't factor, use the quadratic formula. It works for trig functions just as well, only then, rather than variables, you'll have a trig function. So let's see one. Example 4. Okay? Find all the solutions of this. There's the one that we saw in the previous thing. 2 sine squared x minus sine x minus 1 equals 0 in the interval 0 to 2 pi. You can count 0, but don't count the 2 pi. But everything up to 2 pi. Okay? Now, if this were a regular variable function, let me call it 2u squared minus u minus 1, what would we, is equal to 0. It's got to be an equation. What would we do? We would try to factor, okay? We're going to do the same thing here. So let's see. We're going to do trial and error first and see if we can factor it. It's going to be equal to 0. We're not changing anything. We're just factoring it. We change how it looks, and that's all. My pen is doing better today than it has, but it's still being a little problematic. Now, what's the only factorization for 2 sine squared? Sine x times 2 sine x, right? When you multiply what I'm doing is I'm unfoiling it, okay? We started with it foiled, we're going to unfoil it. You start with the first term, the only possible factor for 2 sine squared x is sine x times 2 sine x. Because when you multiply those two together, you get 2 sine squared x, right? Okay, that's the F. Let's go to the, we don't spell it right. We go to the last term now when you're unfolding. Look at the sign of the last term. What is it? I just circled it. Negative. What does that tell us about these two signs? They've got to be different. So do you want plus minus or minus plus? You've got to have them different. Plus minus. So we'll put the plus here and the minus here. Now I'm going to take off my underlines there because it's looking confusing right now. So I'll take that out. Now, the next question is really easy. What's the only factorization for 1? 1 times 1. Got it. Now, I don't know if we factored it right. How we check it is foiling. So sine x times 2 sine x, sure enough, that's sine squared, 2 sine squared x. We knew that. But when we do the outer term, now we're going to spell it right, you get a minus sine x. When you do the inner term, you get a plus 2 sine x. When you add those together, you get a plus sine x. Close, but no cigars. We want it to be a minus sine x. You got the right number there, the right term there, you just have the wrong sign. So guess what that means? What we need to do is change our signs. Make this the plus and make the other one the minus. Okay? Now let's do our foiling again. Sine x times 2 sine x is still 2 sine squared x, right? Now we have a plus sine x minus 2 sine x. Those add to be minus sine x, right? And then the last you have plus 1 times minus 1 is minus 1. All three check out. So we've got a happy face, right? Now, what do we do with that? Okay, I'm going to take away my happy face. Not that I'm not happy anymore. I'm really delighted. But what do we do with this now? You have two entities multiplied together equals 0. What does that tell us? Either this thing times that thing is equal to 0. What does that tell you? Help me, somebody. Any time you have two entities, A times B equals 0, what does that mean? Either A is equal to 0 or B is equal to 0, right? Can you get two things to multiply to be 0 and one of them not be 0? Try it. If you come up with something, you win the Fields Medal, which is the highest prize ever awarded in mathematics. They don't have a Nobel Prize in math, so Fields Medal is all you got. You can't do it. There's no way to have two things multiplied together to give you 0 unless one of those is 0. So what does that imply here? Either this one, which is sine x minus 1 is equal to 0, or the other one, 2 sine x plus 1 is equal to 0, right? The only way you could get the product of those two is equal to 0, one or the other of these, or both, have to be 0. Okay, so let's deal with this first one first. It looks pretty ugly, so I'm going to see if I can clean it up just a tad. There, it's a little bit better. Okay, how would you solve this? Again, you're solving for sine x, not for x. What would you do? Trying to isolate the sine x. Get it all by itself. Add 1 to both sides, right? Is that what you said? Okay. And this goes away, so now we have sine x is equal to 1. All right. We have to figure out what values for x. Now you solve for sine x. Now we're going to try to solve for x. What values of x in between 0 and 2 pi, when you take the sine of it, you get 1. Would it help to draw a little graph of the sine function? Say again? That would be helpful, or you know the answer? Okay. Sine always starts at 0. It goes up, down, and this is 2 pi over here. The only place it reaches 1 is at pi halves. It's 0 again at pi, minus 1 at 3 halves pi, and back to 0 at 2 pi. But we're not counting 2 pi. We are counting 0. The only place it's equal to 1 in that interval is at pi halves. So x is equal pi halves. Okay, I think we did some of those on the first test, didn't we? Okay, no, or maybe that was the second test, somewhere. Okay, now let's go to the second. So here's one possible solution. Let's go to this side. What you do here, you're trying to isolate the sine x. What's your first step? Subtract 1 from both sides of the equation. I did it with my pen, but my pen's not writing. There we go. Now it's writing twice. Okay? So these go to 0. So now we have 2 times the sine of x is equal to negative 1. Now what do we do with that? Divide both sides of the equation by 2. Okay? And that gives us that sine of x is equal to negative 1/2. Now, this particular graph is not particularly pretty, okay, and don't be agreeing with that too quickly. That's -1 there, +1 here. Minus 1/2 is somewhere about down here, and you see nowhere in the first quadrant or the second quadrant is that true, but somewhere in the third quadrant and the fourth quadrant there is a value of negative 1/2. Now, does anyone happen to know what angle is associated? Sine of that angle has something to do with 1/2. And since they're giving this in radians, give me your answer in radians. If you do it in degrees, we'll figure out what that is equivalent to in radians. The sine of what angle is associated with the number 1/2? In this case, I kind of like to go to the unit circle, or maybe not the unit circle, just a circle. Is it all right for me to do that? We're expecting to get two values from here. Can I change my graphical help here to be that? Maybe I should have left that up, but I didn't. Okay, sorry. Okay, let's go. It's not quite a unit circle, it's what I call a two circle. And the pen is doing all sorts of strange things. Okay, now that, obviously I'm not in the middle of the circle, but we can live with that. Okay, now, sine is in terms of x, y, and r. How would you define sine? I'm going to call it sine u in terms of, this is x. I hate using x because that's that x. This is a different x here. X, y, and r, and of course r is your radius. Okay? And what I was saying, this is, I'm going to call a two circle, not a unit circle. All these r's are equal to 2. Now, you'll see the reason for that in a minute. Okay? You may already see it. But what is sine in terms of x, y, and r? Does anyone remember?
Y over R.
You're absolutely right. Y over r. Now, one thing about r, that's your hypotenuse, it's always positive. And now you see why I use the two circle, because I want the radius to be 2. So that means my y has to be negative. Well, y negative is down here, and it needs to be a -1. So the y is going to be here or here. There is where, those are the two angles, and that's what showed up on my graph there, where y is -1. R is 2, y is -1. Okay? Now, what we have to do is figure out what angle this is. Actually, we're looking for this angle here, but it'd be helpful just to know what this one is. Because this is what we call the reference angle, and that's why I was saying 1/2. That the sine of this angle x, I don't want to use x, let's call it u, is equal to 1/2. I'm not worried about the negative right now, just the 1/2. What would be that u? That would be the same one that would be here. What angle would that be? These two angles are the same.
Is that -π6?
It's what?
-π6.
Okay. π6 is the answer because that's up here, and this will be π6, and don't make it the negative π6 would be this one. But you see, we're not counting negative π6. That's not in our interval. We're between 0 and 2 pi. So we're going from here to here. So this angle right here is going to be π6. Okay? That reference angle. Okay? But before we got to that angle, how far did we go here? The straight line is what angle? Pi. Pi plus π6 would be 7/6 pi. So this will be x. Now this is this x, not those x's. This x is 7 pi over 6. And that's in this interval here, right? Now remember, this angle here is also pi 6. But now you're pi 6 short of what's all the way around the circle. No, halfway around is pi. All the way around is, you're really hungry. So you're going to eat 2 pies. Okay, I'm just kidding. Okay, this gets you the 2 pi. So you're 1/6 pi short of 2 pies. Okay, 2 pi would be how many sixths of a pi? If you had to share those 2 pies with a big family, and you had to divide them into sixths, how many sixths of a pie would you have with 2 pies? How many sixths of a pie would you have with 1 pie? If you had to cut it into sixths, how many pieces would you have? 6 pieces, right? So you have 2 pies, that would be 12 pieces. So 1/6 minus the 12/6 would be 12/6 minus 1/6. It's not that hard. 12 minus 1. Say again? 11 pi 6. Excellent. Those are the 3 values where this equation is 0 in between 0 and 2 pi. Okay? Does that make sense?
Yes, sir. Hey,
First?
Dr. Fowler,
Say that again?
I just was going to let you know that if you hear any background noise, it's just my family, they're getting groceries out of the car.
Okay, I don't hear them at all. I was going to say, if you hear any at my place, we had we're guessing it was more than 120-year-old oak tree back when we were having all that rain earlier, and just raining. The soil just couldn't hold that tree up any longer. It was leaning to the south where it could get more sun, and its weight was just too much, and it laid down one night. Literally, that thing was huge. I could not wrap my arms. If I wrapped around the tree at my height, wrapped around the tree, my arms didn't go halfway around the tree. It was an enormous old oak tree, and it just laid down. Okay, and when it did, it took some of our driveway. It broke some of our driveway. It had already broken some with its roots growing over the years, but that was okay. But when it laid down, some of the roots tore up more of the driveway. And then when they came in taking the tree down, the longest saws they had, they couldn't get through the tree when it was that big. So they would cut as far as they could on both sides and then get their bobcat and just bang against this thing trying to break it in the middle. And when they banged against that, they broke more concrete in our driveway because that's where the root ball was banging against. That's the thing that was holding it in place while they banged. They finally got most of it out except for the root ball. It's still there. It's in our neighbor's yard, so we can't do anything with it. It's in their neighbor's yard. And but anyway, we're having our driveway repaired now. So every now and then you'll hear the dog barking at the people working on the driveway. So I may have background noise too. If this bothers you, I can go to the next bedroom over. It's a little further away from the driveway. Can y'all hear?
I haven't noticed any of your
Okay, and I can't hear any of your family making cheering about having groceries come in. No, okay, whatever they do. Okay. So, any questions on this problem? Let's see how they did it. Okay. Well, we treat the equation as if it's a quadratic equation, but not quadratic in a single factor like u, but quadratic in a function like sine x. So let's see if it will factor. They said it would factor as 2x plus 1 times x sine x, 2 sine x plus 1 times sine x minus 1. Well, let's just check it and see. That's 2 sine squared x. That works. That would be minus 2 sine x plus sine x is minus sine x, and then minus 1. Yes, that works fine. They did it correctly. And that's equal to 0 because the original equation was equal to 0. All you did was factor that quadratic expression. But if two things multiplied together equals 0, that means one or the other of them has to be 0. That's called the zero product principle, by the way. So either 2x plus 1 is equal to 0, or sine x minus 1 is equal to 0. Okay? Well, let's solve either of those. On the first side, we get sine x equal minus 1/2. On the other side, you get sine x equal 1. On the left-hand side here, the one we did second, they're doing first, that gives you two values. They're both in the, one's in the third quadrant, one's in the fourth quadrant, because that's where sine is negative. One is 7/6 pi, the other is 11/6 pi. On the other side, where sine x is equal to 1, is only one value in this interval. There's infinite number of places where it's equal to 1, but in that interval, there's only one place, and that's the pi halves. So those are the three solutions to that quadratic equation in sines. Any questions?
No, sir.
All right. Now, they are skipping examples 5 and 6. So let's go back and we'll do example 5 and 6. So let's see. So this gives me, yeah, that gives me a little more room. So let's use this for example 5. Solve this one. 2 sine squared x plus 3 times cosine x minus 3 is equal to 0. Now, does anything strike you as sort of odd or problematic about this quadratic expression in trig functions?
Has a negative 3, but that's about it.
Say that again.
Has a negative 3 in the problem, or in the equation.
Okay. Yeah, well, negative 3 doesn't bother me so much unless I wrote it wrong. No, I think I did. Okay. What's problematic here? You have two different trig functions here. Yeah. That would be like if I said, solve this quadratic equation. 2u squared plus 3v minus 3 is equal to 0. You couldn't do that, could you? You can't factor it because they're different variables. Okay? But with trig functions, unlike u's and v's that we don't know anything about, with trig functions, we do know there's relationships there. And here's a hint. I think I've said it before. When you see the squares, what identities should you think of? Pythagorean identities, absolutely. Can you remember which Pythagorean identity relates to sine squared?
Sine squared x plus cosine squared x equals 1.
Perfect. Okay. Now, I want that strictly in terms of, I want a sine square out of that. So how do I isolate the sine squared here?
Minus cosine.
Yes, minus the cosine squared x from both sides. Okay, and these go to 0, and you get that sine squared x is equal to 1 minus cosine squared x. So that's what I'm going to put here instead of sine squared x. So we have 2 times 1 minus cosine squared x plus 3 cosine x minus 3 equals 0. Okay. What would we do next? Yeah, let's just, Yes, distribute the 2 across those parentheses. Working with parentheses can be a pain in the neck sometimes, so if you can get rid of them, get rid of them, okay? So, but don't just erase them, okay? So that would be 2, and then you distribute this, and you get minus 2 cosine squared x, right? And my pen is messing up by putting extra lines in there. So let me see if I can get those out. Okay. Plus, now it's not writing at all. It got mad at me. Okay, there it is. 3 cosine x minus 3 equals 0. Now, that actually looks a little worse because you have 4 terms, but the good news is all the variable functions are in the same function. You've got all cosines in there. No more sines. But what can we do to fix a little bit of what we just did? What would be your next step? Say again? I wouldn't quite factor yet because you have some like terms you can combine, right? Okay. And here's the other thing. I really don't like having a minus as my leading term. Because this is an equation, I can also either move everything to the other side as I'm combining like terms, or you could say just multiply everything by minus 1, because 0 times minus 1 is still 0. So if it's okay, I'll do both of those at once. So this becomes a 2 cosine squared x. I'm either moving it to the other side or multiplying by minus 1, whichever you want to do. This becomes a minus 3 cosine x. Now, when you added these two together, they became what? 2 plus the negative. Say again? Negative 1, but now since we're changing sign, that becomes a plus 1, and that's equal to 0. Was that legal in most states?
Yes.
Yeah, I think we can get away with that. Now is when let's get around to factoring it. So let's see if that will factor. I may not have left enough room here. What's the only possible factorization for 2 cosine squared x? Cosine x and 2 cosine x. Perfect. Okay. Now we look at the sign of the last term. It happens to be a plus. What does that tell you about these two signs?
One of them is a plus.
Say again?
One of them is a plus sign.
Okay, no. For that to be a plus, these two have to be the same signs. Right? Because plus times plus gives you plus. Minus times minus gives you plus. So they have to be the same. If you had only one of them being plus, the other minus, that would give you a minus. Right? Understand what I'm saying?
Yes.
Okay. Now, so you know they have to be the same to get a plus here. Look at the middle term. What sign is it? Negative. That means both of these have to be negative. Now, the next is a very easy question. What's the only factorization of 1? 1 times 1. Okay, good. Now, let's see if we did it right. We sure hope so. Cosine times 2 cosine would be 2 cosine squared. That checks. And then you do that was the first. The outer is minus cosine x. The inner is minus 2 cosine x. Those add to be minus 3 cosine x. That checks. And then the last, minus times minus, is plus. Yes, we did it right. So again, we get a smiley face. We're happy, right? So let's clear those out of the way. I can't get them to clear. There they, no. Oh, they went. Okay. Can't get my pen to come back. Okay. Now what do we do with that? Is what?
So, make it equal to 0.
Okay, make each one of those equal to 0. Either cosine x minus 1 has to equal 0, because the product of two entities to be 0, one of them's got to be 0. Or 2 cosine x minus 1 equals 0. Okay? How do we solve that first one? Oh, and by the way, did they give us a range on this one? I don't think so. So we're going to have to give a general solution on this one. Okay? So what will we do with this first equation? Add 1 to both sides. Okay? I can't write too much more at the bottom, so I'm going to come up here and write. So cosine x, when you add 1, these go away, is equal to 1. Now, where is cosine x equal 1? Would a picture of the cosine function be helpful? The graph.
Yes.
Okay, let's do that. So I'll try to keep it sort of small up here so it won't get in the way. Cosine starts where?
Starts at 1.
1. You're absolutely right. There's your answer right there. It's 1 there, then it goes down to 0, minus 1, up to 0, and back to 1 at 2 pi, because the period is 2 pi. So, the cosine x is going to be 1 at every 2 pi. It'll be at 0, 2 pi, 4 pi, 6 pi, 8 pi, negative 2 pi, negative 4 pi, negative 6 pi, negative 8 pi. So this is going to be true. X equal 2 n pi, where n is any integer, positive or negative. That's it. That's the only place where x is equal. Where cosine x is equal to 1, x is a multiple of 2 pi. Does that make sense? Okay. Let's do with the second equation now. What would you do with it?
Plus 1.
Add 1 to both sides. You're right. And that gives us, I'll write it up here, 2 cosine x, no, these added to 0, is equal to 1. Then what would you do?
Divide 2.
Divide both sides by 2. Here the 2's go out. Okay, they're slow, but they go out. And you have cosine x is equal to 1/2. All right. Now again, I don't know if this will be helpful or not, but here is, if that's plus 1 up here, this would be plus 1/2. So there's going to be an angle right about there where cosine x is equal 1/2, and then another angle over here. Now, any idea where those angles are? This, by the way, here is pi halves here, because this is pi here, and this is 3/2 pi here. Those are the key points there. Okay? And this is something short of pi halves. Not much short, just a little bit short of pi halves. Any ideas? How much short? Okay.
5/4.
Say again? Well, let's just think now.
5/4.
I can't hear you. Say again?
5/4. Is that where it's at?
Okay. I couldn't quite make out. I heard you, but I couldn't make out what you were saying.
I said pi
Pi quarters. Is that what you said?
Yeah, 5/4.
Okay.
Is that where it's at?
Pi quarters, which would be halfway in between. I can't get my pen to write right there. That would be pi quarters. At pi quarters, the cosine and the sine are square root of 2 over 2, which is just a little bit more than 1/2. So not quite. So it's not pi quarters, but it's in between pi quarters and pi halves. That would be pi
Thirds.
thirds. Very good. So this would be x equal pi thirds, okay, or x equal, now over here, you're just past 3 halves pi, and guess how far past 3 halves pi you are? Well, let me put it this way. This is the angle pi thirds that gets you here. So this would be the angle pi thirds back here. I mean, that's not the angle, but I mean, that's how far you are from 2 pi. See, pi thirds is how far you are from 0 here. So that's how far you are from 2 pi here. So what's 2 pi? Or how many thirds are in 2 pi? If you had 2 pi's and you cut them into 3 pieces each, how many pieces would you have? Okay. If you had 2 pi's and you cut them into 3 pieces each, how many pieces would you have? Think food. Don't think trig. Think food. If you had 2 pi's, cut them into thirds, how many pieces of pie would you have? Cut each one into 3 pieces, how many pieces of pie would you have? It's not that hard, okay? If you had 2 pies, you cut them into 3 pieces each, how many pieces of pie do you have? 2. Okay.
6.
6 pieces of pie, right?
Sorry, that took me a minute.
Huh? What'd you say?
Sorry, that took me a minute. My brain went dead.
Okay. All right, you have 6 pieces of pie. So you have 6 thirds of a pie when you have 2 pies, right? Okay. And you're going to be 1 pie short of that, 1/3 pie short of that. So how many thirds of a pie do you have? Had 6 with 2 pi, lose 1/3. How many do you have left? 6 minus 1. 5/3 pie. Okay, does that make sense? All right, so there's the other place. But here's the problem, folks. We're not limited just 0 to 2 pi. We want all of them. Well, this one right here is going to show up again over here, which is exactly 2 pi away. This one will show up when you go down here and come back up here again, and that will be another 2 pi away from this. So each of these is plus 2n pi, and this is plus 2n pi. Because it's not just plus 2, it could be minus 2 too. That n could be negative. So this one would be, when you go back over here, back here, no, somewhere back there, you have this one again. I didn't draw far enough. I ran out of room. This one would be this one right here. Okay. Yeah, no, this is right. I was right in the right place, right there. Okay. So that's why we put the general solution. What in the world is this? Okay. 2n pi, pi thirds plus 2n pi, and 5/3 pi plus 2n pi. Those are our 3 solutions to number 5. Let's see what the book got. 2n pi, pi thirds plus 2n pi, and 5/3 pi plus 2n pi. And that one is also followed by a checkpoint. Okay? Always, if you can, do the checkpoints sometime shortly after class. Okay. Now, any questions on this before we move on? All right. I hope my way of trying to finding those angles isn't more confusing than it's worth. sounds like it's confusing you. I didn't mean to do that. But it's just, I like to think in terms of food. So anyway, I'm playing on the words pie. Okay. So anyway, let's erase all these and go for example 6. Now, even though it's not on the PowerPoints, you can go to larsonprecalculus.com and see an interactive version of this type of an example. Now, this one's a little bizarre. Here's what we've got. Cosine x plus 1 is equal to sine x. And you want to find all the solutions for that on the interval 0 to 2 pi. So in one complete cycle for x. So we won't have to have our 2n pi's or anything like that at the end. We're going to actually get some number of solutions here. Now, what's wrong with this problem? There's actually two things that are sort of wrong with this problem. Number one, you got two different functions here. Okay? And they're sines and cosines. And if you had two functions, you would want them to be, at least one of them, to be squared. But they're not. And there's no identity that relates sines and cosines directly. Okay? You might say, well, sine divided by cosine would be tangent, wouldn't it? Well, if you divided everything by cosine, that would become 1, that would become tangent, but this would become a secant. And then you still have two functions, so no, that doesn't help you either. What do we really want? We want one of them to be squared. Now, how can we go about squaring either one of those? How about this? Square both sides of the equation. You think that might work? It sure seems like it. Here's the problem, though. Now, this worked in algebra. It also works in trig. Anytime that you square both sides of an equation, whether it's a trig equation, an algebra equation, or any kind of equation, you may be introducing what they call extraneous roots. That means you may have just created something that looks like it's a solution, but really wouldn't be. And here's an example. What if sine x were 1, okay, and cosine x were 0, then you'd have 1 is equal to 1. That should work, okay? But what if you had sine x is equal to minus 1 and cosine x equals 0? Then on the left-hand side, before you squared, it would say 1 is equal to minus 1. You say, no, that doesn't work. They're not equal. But when you square them, you square a minus 1, you get 1, and you square a 1 and you get 1, and now you think that does work. So you see, you just introduced a possible wrong answer. Okay. So what does this mean? We're going to go on and do it, but at the end, you've got to check every answer, not by the squared equation, but the original equation, and make sure it works correctly. So that was all what that was about. So let's square both sides. What happens when you square this binomial? What would that turn out? Anyone know? Cosine squared x. That's a good first start. Anything? Plus. Okay, I agree there's a plus 1 out there. But I contend there's got to be a middle term. Okay, it's going to have a cosine in it. I agree with that. But what else does it have to have? 2. Okay, that's because when you square a binomial, you square the first term, twice the product of the two terms, square the last term. So, yep, that's correct now. Okay? And this is equal to sine squared x. I like that. Nothing else to do to that one. Okay. Okay, now we're back in the similar boat to what we were before. We have an equation. You still have two variables, but at least one of them, two of them have squares, but this one doesn't have anything but a square. Does anyone remember what sine squared is in terms of cosine? We did the same thing earlier. What was that? Say again? What is sine squared in terms of cosine? And Pythagorean theorem, if that's what you said, that's exactly what you use.
Cosine squared minus 1.
No, reverse that. No, not that reverse. 1 minus cosine squared. Okay? Because if you add cosine squared to both sides, you get sine squared plus cosine squared is equal to 1, and that's true, right? Okay. Now, so here we have a cosine squared x plus 2 cosine x plus 1 is equal to 1 minus cosine squared x. What would you do to solve that one? Anytime you have quadratics, say again? What did you say? Okay, not yet. You need to get everything on the same side equal to 0 before you factor. That 0 there, that's the key. You have to have it equal 0 before you factor, because 0 is the only thing that you have a zero product principle for. There's nothing else that you can say, oh, that's always going to be this. It's only if that answer is 0. So don't factor until you get everything on one side. Hint, what would you do next? Say that again, a little louder. Okay, and how would you do that? I can't hear. Say again?
So you would subtract 1.
Subtract 1 from both sides. I like that. Anything else? And add a cosine squared x to both sides. I like that as well. Okay? And here your 1's go out on both sides of the equation, don't they? Interesting. And the cosine squareds go out on this side, giving you a 0 over here is exactly what you want. But on this side, what do you have left? Say again? 2 cosine squared x, is that what you said?
Yes.
Cosine squared x plus cosine squared x is 2 cosine squared x plus 2 cosine x is equal to 0. Okay? Now we can proceed with our factoring, now that you got 0 on that side. What would you do to factor that? Any ideas? Okay, no, okay. Don't do that because you could be dividing by 0. But if you factor them out, that's a different issue. Factor out a 2 cosine x. And what do you have left in the first term? Cosine x. And what do you have left in the second term? Plus 1. Perfect. Okay? If I could get it to right there, it goes. And that's equal to 0. Now, I'm going to take care of one thing for you right now, and this one is legal. You can divide by 2. If that's what you're suggesting, then I should have let you do that. You can divide by 2 because 2 is not equal to 0. If you divide both sides by 2, you wind up with just cosine x times cosine x plus 1 is equal to 0. Because if you divide this by 2, that goes to 1. divide that by 2, and you still got 0, okay? So you're back where you started. So what you have now is either cosine x is equal to 0 or cosine x plus 1 is equal to 0. Right?
Yes.
Okay. Let's start with the first one. Where in the world is cosine x equal to 0? Would it help to draw the cosine function? Where does cosine start? At plus 1, goes down to 0, up to 0, and back to plus 1. At plus 1 there, we're not counting the 2 pi here. This is at 2 pi. This is at 0. So this one right here would be at pi. So this is right here. Halfway in between, this would be pi halves, and this would be 3 halves pi. I think we just found it, didn't we? There's our 2 zeros. And that interval is at pi halves and 3 halves pi, right? That's where that's equal to 0. You agree or not? X equal pi halves or 3 halves pi. Now you don't have to worry about the n pi's because it says only in this interval. Okay? We found the only 2 places there. Let's deal with the right-hand equation. What would you do with that?
Minus 1.
Subtract 1, is that what you said, from both sides? That makes that go away, and then you have wound up with cosine x is equal to minus 1. Where in the world is that true? Huh. Didn't realize I was giving you the answer. Where is cosine equal to negative 1?
On the bottom side of the
Say again?
vertical axis.
At pi, right there. There it is, at minus 1, right there. You see it? So x equal pi. So there, and that's the only place in between 0 and 2 pi where cosine x is equal to minus 1. And x equal pi. So there we have it. X equal pi halves, pi, or 3 halves pi. And, oh, okay. But we can't say those are our answers, can we? Remember, we have to check them because we squared both sides. So let's write down our original function again. Cosine x plus 1 is equal to sine x. It's always a good idea to check your answers. In this case, you have to check your answers. So let's choose the first one, pi halves. So what's cosine of pi halves plus 1? Is that equal to sine of pi halves? That's the question. Anyone know what cosine of pi halves is? We did it right here. What's cosine of pi halves? What is cosine of pi halves? Up at our graphic. It's 0. 0 plus 1, is that equal to, what is sine of pi halves? Would it be helpful to draw the sine graph? Or do you know it? Say again? Okay, so let's draw the sine function here. Where does sine start? It starts at 0 at the origin. It goes up, down, and up. And that's where it goes in one cycle. So it makes it to plus 1 where? This would be 2 pi. This would be pi. This would be pi halves. right? Well, sine of pi halves is 1. Is 0 plus 1, 1?
Yes.
Yes. So this works. So this answer is correct. Pi halves works. Okay? Which you want to try next? Pi or 3 halves pi? Pi. Okay? So let's see. Cosine of pi plus 1, is that equal to sine of pi? That's the question. What's cosine pi? I'm going to erase some of my ugly scratching up here. Oh, how did that happen? Okay. 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 Cosine of pi. What was cosine pi? Here's the cosine function. There's pi. What's the value here? Help me, somebody.
1.
It's -1. This is -1 plus 1. Is that equal to sine pi? What is sine of pi? Here's the sine function. There's pi. What's sine of pi? No, sine of pi. Here is the sine function. There's pi. What's the sine function at pi? When x equals pi, what's the sine of pi? It's right there. What's the y value? Say again?
Y value.
What is the y value? Huh?
Pi halves.
I can't hear.
Pi halves.
Why isn't pi halves here? What's the y value there? Anywhere on the x-axis, what's the y value? Is it positive?
0.
It's 0. Well, is -1 plus 1 equals a 0?
Yes.
Yes. So therefore, this is the correct answer. Hey, we're doing pretty well. Both of the first two we checked were fine. I can't get them to check. My pen is not cooperating at all today. Oh, now they checked. Okay, well, I wasn't looking. Well, we better check that last one too. I bet you y'all think it's going to work, don't you? Let's see. Cosine. My pen is not working. Okay, it is now. Cosine of 3 halves pi plus 1, is that equal to sine of 3 halves pi? Okay. Well, what's cosine of 3 halves pi? I can't hear you. What'd you say?
Wouldn't it be 0?
That would be 0. Okay. Plus 1. Is that equal to sine of 3 halves pi? What is sine of 3 halves pi? There's 0, pi halves pi. This is 3 halves pi. And that's 2 pi. What is sine of 3 halves pi?
No, be 0. No, -1.
-1. Okay. Is 0 plus 1 equal to -1? No. But you see where the error showed up? When we squared both sides. You square +1, you get 1. Square -1, you get 1. That made it look like they were equal. And they're not. Okay? So you have to throw out this one. The other two checked, but the 3 halves pi did not. So anytime you square both sides of an equation, you always, that's not just in trig equations, any kind of equation, you have to check your solutions to make sure you didn't introduce a false solution. So the answer is pi halves and pi. Perfect. And guess what? There's a checkpoint as well. Okay. Now, question is, were there any questions on that? You need it up there a little longer. Anybody?
Yes, I need.
Say again? Are you still writing?
Yes.
Okay. Let me know when you're through. All right, both of you? Okay. So let's erase this one. Well, we didn't have to. We could have just, let me guess. Let's just advance until we get to functions involving multiple angles. Okay. Now, someone clue me in. How much time do we have left?
I have a minute. Less than a minute.
1 minute? Is that what you said?
Less than a minute.
Okay.
Less than a minute.
I can't hear you.
It's 11:15.
Oh, it is 11:15. All right, we're going to have to pause there then. Okay, and we'll pick up next time with functions involving multiple angles. Top of page 367. Okay, let me put a mark in place. Okay, and we still got a ways to go, but not too far before we finish 5.3. Homework exercises in 5.3 would be any of the odds 5 through 9. They're all at Calc Chat. Any of the odds 11 through 27, they're all at Calc Chat, with 13 at Calc View. Any of the odds 29 to 37, they're all at Calc Chat, with 29 at Calc View. And stop right there, because then we'll pick up with multiple angle equations next. Okay? Any questions? All right. Now let me just do a little bit of review here. I don't have much time because I have another class starting soon. 2 people have turned in research papers. One of you are here and one of you is not here. All but 1, 2, 3, 4 people have turned in the first test. One of you is here and one of you is, and some are not here. The second test, only 1 person has turned in. So there's a bunch of deliverables, and guess what? We're in our last month of class, okay? So please start getting this material in, okay? Sooner rather than later. Research paper can come in anytime. Test 1 should have already been here. Test 2 should be coming in anytime too. So please try to get those caught up as soon as possible. Any questions?
No, sir.
All right. Well, I want you to have a good weekend. Of course, working on trig will make it good, right?
Yes, sir.
Absolutely. So have a good weekend. David, I'll see you in a couple hours, right?
Yep. See you.
Okay. Take care. Have a good weekend, Thomas.